45 minutes is a tough goal for somebody like me. I keep talking. So I will give you a talk today about our recent work in uncertainty quantification. And specifically, I want to give you two different definitions or different perspectives on generalization. So I do reinforcement learning, so hardcore machine learning. And the guiding question that I was always looking into was, what do you know when you don't know what to do? What do you do when you don't know what to do? So if you're an autonomous agent and you have no idea what to do, so what do you do then? I'm looking at this through the lens of reinforcement learning. So it's essentially, we have a system where the agent observes stuff from the environment, and then we give it during training some rewards, and then we expect it to kind of learn how to optimize those rewards. However, this works all awesome if we have tabular representations of our state space. As I assume in most of your research, it also kind of works as soon as things are tabular. But in practice, this is of course not really scalable. Like, no interesting problem in reinforcement learning can be solved by learning the Q values of a table of states and actions, of discrete states and actions. So what we do instead is we train neural networks to do the same things. I'm not going to go into detail today about like what these things are, but I want to basically talk about the neural networks themselves. So what can they do? What can they not do? In which situation can we actually expect these things to predict something that is even close to the truth? And in which situations we definitely cannot. So the main issue is that the AI that we are working with, and the definitions differ here. So I'm assuming that some of the AIs that some of you will be working with are not affected by this, but at least the version of AI that we are working with always tries to learn something from the real world by interaction usually, and encode this somehow in neural networks. And neural networks are really, really good at estimating or at interpolating between known things. So you probably have seen a figure like this, where you basically say, these are your data, these are data points, you try to classify them. And it is very good to basically solve something. You ask it like, what is the class of this point here? This is usually what neural networks are excelling at. However, if we're looking into the real world, like we're training our robots in some environment, then it becomes pretty clear that no two situations are exactly alike. And it's very, very easy to produce a situation that is formally very far away from the training data, even though practically nothing has changed. If I would put a poster on the wall of this office, my robot would no longer be close to any of the training data points, even though nothing really has changed. Like, the control shouldn't have shifted by that. And this is really a problem because in the real world, you can just, it's very easy to just move some chair that you haven't moved during training, and all of a sudden everything's wrong. So what I will do today is I will quickly go through the idea of like, how do neural networks generalize anyway? Then I will talk about how we are usually estimating epistemic uncertainty to estimate how much we can rely on our predictions. And then I will basically show you that this is not enough, and give you an idea of like another way of defining what we know or what we think the neural network knows. So how do neural networks approximate? Well, don't read the theorem. This is an old thing from the 80s. It basically just says that if you have a shallow neural network that is wide enough, then this is a universal function approximate. Any continuous function can be learned. But in practice, we don't use shallow networks. Like, we all use deep neural networks to some degree. And this is because we have empirically found, and that's actually not that old, it's like 20 years ago or so, we empirically found that the deeper you make your network, so this is the number of neural network layers, the better the performance gets. So this is the test accuracy in some simple classification task. And the big question is like, why is that? Like, how come that if you can already represent any possible continuous function, that apparently, with a shallow network, that apparently making them deeper helps? And to answer this, we first need to kind of go from the outside and ask ourselves, like, okay, why do shallow networks actually work? And so basically the idea here is to say that, and I will differentiate between interpolation and extrapolation in a second, that if we are close to the data, like if these are, so this is our training data and we want to know what is the prediction of this sample, then our neural networks actually can look into, like can compare the similarity of previously seen training samples with the test sample. So mathematically, this is sort of described by the Cauchy-Schwarz inequality, or in a more general sense, by Lipschitz continuity of the neural network, which essentially just means that there exists, so for every neural network, there exists with finite parameters, there exists a finite Lipschitz constant such that you can bound the difference between the function output between two samples by as a scaled version of the Euclidean distance. So the insight here is to see that fundamentally, just by the fact that they are continuous or Lipschitz continuous functions, neural networks are good at learning to assign similar outputs to similar inputs. And this is why interpolation works really well. However, we often are interested in the setup of extrapolation. That is like a sample that is very different from, like in the Euclidean sense, very different from what we've seen so far. And here, the important concept is that of invariant or invariances. Technically speaking, it's equivariances, but equivariances is like another set of equations. So just like let's concentrate on invariances because it's easier to understand. So an invariance is basically we're saying a function is invariant with respect to a group or class phi if for any mapping in that group phi holds that f of x equals f of phi of x. So if I'm saying my function is invariant to rotation, then the output of the function must be the same no matter how much I rotate the image. So this is important because neural networks are essentially linear functions that are interrupted by nonlinear activation functions. So, for example, you usually have like linear modules, and then you have like a ReLU nonlinearity that just zeroes out all the negative outputs of the linear function. So why is this important? This is important because this nonlinearity is producing an invariance. So here I have this example. This is not a ReLU. This is an absolute function which nobody uses, but it makes a very nice picture. So this is why it's here. If you take a linear function and then you take the absolute value of that output, then this is effectively the same as if you take like this. This line is defined by the linear function, and the absolute vector is just taking the negative output and maps it to the positive output, just the same as if you would take the space and would fold it. So now you have twice as many data points in the space where where the data has been folded into. And you can do this again and again and again, and every single time you effectively take like a huge input space and just fold it upon itself until it's all of the data is so concentrated that you can actually do interpolation in it. So this is kind of the interpretation of like, why do neural networks extrapolate? Because with every layer, the interpolation gets better. And then if these linear functions in the lower layers are defined correctly, you can learn how to extrapolate to things that you have never seen before. So let's go and ask ourselves, how are we going to use this? Or like, why is this an important question? So first of all, I want to define epistemic uncertainty. So this is a little bit contentious. And it mirrors the question of like, what is extrapolation versus interpolation? And it mirrors the question of what is out of distribution versus in distribution. Because there's lots of different definitions of what epistemic uncertainty is. The only thing that everybody is kind of agreeing on is that it is going like epistemic uncertainty goes down when I observe more things. What I observe, this is all a little bit fuzzy. So the basic idea is the following. This here is just like an example from a Gaussian process where all of these dots here are training data points. And I want to estimate something. I think the dashed line is actually the target function, and the solid line is the mean of the Gaussian process. And so what we're basically doing here is we're just saying where we have data, we trust our prediction, our interpolation prediction in a way, but we'll come to this in a second. And where we don't have data, we just, the epistemic uncertainty grows and grows and grows. So why do we want this? This is now goes a little bit into the reinforcement learning direction, but I'm pretty sure that if you're using neural networks, you will have a similar problem. So we do this because we need to make reliable predictions, we need to kind of upper and lower bound stuff. What I'm doing here is I'm using the Chebyshev inequality. And what I'm using it on is the so-called Q function, which is just the estimation of the future return that the agent or the robot will see. And I'm basically treating this as a random variable. I'm saying like, okay, every single time that I'm randomly initializing my neural network and I'm letting it learn, it's going to learn something. And if I'm doing it 10 times, I'm getting like 10 different Q functions. They will all be subtly different, right? They're not going to converge to the same thing. And so I'm just treating them here as a random variable. And I'm using a Chebyshev inequality to say that, well, I can over or underestimate, like if I know the variance of this training process, if I know like how sure I am about the result that I get at the end of the training process, I can bound the observe plus some upper or lower bound based off the epistemic uncertainty. And I can use this to bound the true expected outcome of the process, which I assume is the correct output because I assume that my training process is unbiased. And I can do this with high probability and so forth and so forth. The details are not as important here. The important thing is to understand that if I want to know, or if I want to make a fairly certain estimate saying that if I'm going to go this way, it can be at most this worse. Like this is the worst thing that can happen. I need to compute these bounds. I can't just rely on whatever my neural network tells me because my neural network could be strictly wrong. So the point here is that we sometimes need to over and sometimes need to underestimate these things using the epistemic uncertainty. So secondly, then what I want to talk about is ensembles. Ensembles are one of the vanilla, or like the classical ways of estimating uncertainty with neural networks. So the idea of an ensemble is that instead of just doing one optimization process that leads to one neural network parameter set, you run you initialize every neural network randomly in the beginning anyway, right? Like this is how you train neural networks. And what you do is you train a set of neural networks on the same training data, or at least with the same training process, and you end up with not one, but with a distribution of possible parameters, or a set of possible parameters to be exact. So why is that? This is because neural networks have a weird property. That's the loss function of neural networks do not have a unique minimum. All loss functions have a large set of possible local minima. And these minima are, so first of all, a large set of global minima, but also additionally a large set of local minima. So every single time that you're going to train something, it will fall into a different local minimum. Sometimes it ends up here, sometimes here. And the only thing that you get basically from this is that the likelihood of ending up in these minima depend on your optimization procedure and the scale of the optimization landscape. This means that you can actually think of epistemic uncertainty as, let's just train the same problem 10 times and then take the variance of those predictions. Because that's a very common, basically by now a gold standard of like how you should estimate how sure a network is. The other perspective on this is the neural tangent kernel. So who here has heard the term neural tangent kernel? Very few people. Okay. So this is one of the few pieces of theoretical neural network learning that we actually have. So one of the few descriptions of how neural networks learn that we can actually analytically compute or express. And the basic idea here is that you can you can do a linearization of your neural network using just a simple first order Taylor expansion. And then you can rewrite the learning procedure in terms of these neural tangent kernels, which are simply the inner product of the gradients. So you just look for this input x, in which direction of the parameter space do I have to move so that the function output gets higher. We don't have a loss function here at all. It's just a function output. And it turns out that if we mathematically let the width of a neural network go to infinity, so it goes wider and wider and wider, then this kernel becomes constant over time. So it actually becomes a kernel that we can analytically use. And as a result, we can actually describe the theoretical evolution of an infinite ensemble of neural networks with infinite width. It's a lot of infinite assumptions here. This is, of course, completely unrealistic, but we'll see in a second that this actually works. We can describe this as a Gaussian process. Who here has heard the term Gaussian process? Okay, more, great. So essentially a Gaussian process is just a distribution of the functions that you can condition on observables, and then under certain assumptions, you get like a mean and a variance of this. This is the mean. We'll basically just see that the mean of it is just, wherever you started, and then you just learn this is just the mean of a kernel regressor or of a Gaussian process. So the interesting thing is that this Gaussian process is also giving us a variance. So this is the mean of the Gaussian process. So on average, you expect your ensemble of neural networks to converge something that makes these predictions. But we also have a variance of the Gaussian process that is equivalent to training this ensemble. And the interesting thing about this is that it is strangely computable. So we have here this is just the kernel of, so let's say like this. This is the variance of a infinite ensemble of functions at the test sample x dash. And this is just the kernel of x dash with itself, which is just, remember, it's just the inner product between the gradients of the function at this point. So it's totally computable. takes a forward pass. It actually takes a forward and backward pass through the model, but it's totally computable. And this here is sort of the rest of it, and it contains this ugly. So this here is actually the set of all training samples, X, with calligraphy large X. And this is therefore a number of training samples times number of training samples matrix that you don't want to invert. So this sounds, at first, this sounds not really computable. But what you can do, the question is like, can we still get this somehow? And the answer is yes. I will go to the second how this works, but just here, these two graphics are, these are the training data points on a two-dimensional plane. And the color here represents the variance of a ensemble of 100 models. We just do like, regression here. Nothing complicated. And these are just the same thing, just like plotted from different perspectives in a 3D plot. And what we want to learn a function g, this function here, such that just by, without training 100 models, just by training this one function, we want to estimate the same uncertainty. This sounds like a tall order, but the interesting point here is that if I'm going back one slide, and I'm looking at this equation here, if you ignore the initialization, if you just assume for a second that the initialization is 0 everywhere, then this is just kernel of the test sample type and the training samples, this terrible inverted inner Gram matrix here. And then, like, if this is 0, then this is just like the labels. So the most important observation here is that if we're looking at the variance, this looks pretty much like the function that we need. The only difference is that instead of labels, we have these kernel outputs here. So in our current iClear paper, one of the two iClear papers that are dealing with this, we just do this. We essentially just we just say this part of the equation here are the labels that we want to predict. So we just set, it's just the kernel output between the sample where we currently are, the training sample that we have, and this has to be a slightly extended set. Don't want to go too much into detail here, but the essential bit is just to see that, well, if this is the theoretical output of a regression problem, of this regression problem, then we can just train this regression problem and we get a function g out of this that has the same properties as the variance, or this part of the variance, of an infinite ensemble of neural networks. And then you can just use this in the end. Like if you have learned this G, you can use it in this way. I want to give you one application example. Again, this is from our domain, so it might be a little bit far away from what you're used to, but it's, so this is Wisdom. This is what the agent sees. It's just like you're playing the computer game Doom from the 90s. This is the map. The goal of the agent, so there's no enemies, we're not very violent. The only goal is there's different starting positions, and we want to go to this goal here. And you need to learn that. And because it's a large environment, it's very easy to get stuck. You need to explore the world a little bit more, and that means that instead of just following the expected return that your neural network predicts, you need to have an upper bound on that. You can get an upper bound on what your neural network predicts, how good something is. You can just always be greedy with respect to the upper bound and eventually explore everything sufficiently until, you know, the upper bound of all of the possibilities falls below the true value of the optimal path, and then you have it. So this is like what we're usually doing. And we basically see, like, for example, here, where we plot against on the x-axis is the number of environmental interactions. And yes, this is 10 to the power of 7. So this is like 10 million environmental interactions, which is a lot for a roboticist, but sadly is the state of the art in reinforcement learning. We see that our method in blue here performs much better. Actually, it performs very similar to another method, which is called random network distillation, which I don't want to talk about, which we are currently writing a paper that proves that this is also equivalent to the variance of an infinite ensemble. This is supposed to demonstrate that, yes, these kind of things that we are computing here are actually useful in practice. And the downside of this is that we're currently only predicting the variance, or how much we know about the functions themselves locally. But what we actually are interested in is how sure are we about the entire future that this function is supposed to encode. So the next step that we took was to ask, what is the problem if we're actually trying to estimate not just an ensemble of the local functions, like how sure are we locally about this function, but also how sure are we about the entire future that the function is encoding. And the basic problem that we're facing is that the labels of that function depend on the future. If we act differently in the future, then the labels become different. And as a result, the label distribution becomes non-stationary. So I'm not sure how many of you are familiar with the Böhmer equations, but these are the labels that we are using in a Böhmer equation to estimate what is the future return of choosing action A in state S. That's all. And there's like two major sources of non-stationarity here. One of them is the future, like the value, or like the return of the next state that you end up in, also depends on the function you learn. So if you change your function, you change your targets, which make your targets or your labels non-stationary. And the second one is that this is the optimal Böhmer equation. So we're basically always choosing, in the next state, we're always choosing the action that maximizes that return. So we are essentially also have a non-stationary policy that we're optimizing over, a non-stationary way of choosing actions in the future. And both of these are kind of screwing with us. So we found a way around this via what's called a universal value function. So a universal value function basically is not a normal value function. You know, what you're learning here depends on the reward. This is this R of SA here. And this is basically because we want the agent to learn a policy, or like, you know, a behavior that maximizes the return of this reward, the sum of this reward in the future. Universal value functions kind of turn this around and say, like, let's just say, I don't want to learn the value function for one reward function. I want to learn them for a bunch of different reward functions. So I have this additional parameter, z, which indicates which reward function my value function is currently representing. And the simplest way of thinking of this is if you just say, if I want to learn a universal value function that tells me how can I navigate to any location in this room, I would simply declare any location in this room to z. And then I can just compute, well, if this here was the location I wanted to go to, if this is the location encoded by z, then I'm getting a reward of 1. In all of the other states, I'm getting a reward of 0. I can do that with all locations, and then all of a sudden I can just plug in any z here, and I'm getting estimated optimal return to get to that state z. This is important because while this thing here in state action space is non-stationary with respect to the ensemble variance that we're interested in, this set of states, actions, and goals becomes stationary. It's kind of a little bit tricky to wrap your head around, but it is that particularly this choosing the maximum action here becomes a stationary process, because now there exists, for every input Z, there exists a unique optimal policy for this case. So what we're doing now is the only thing that's still remaining is that the value chart changes over time, and we found a way, and I don't want to go into math here because it's just like it's too much. The papers are very interesting. Please have a look at them. This is the second iClear paper that describes this. But the math is really involved, so let's just skip it here and just say that if we do this, we can basically learn again for these extended return functions, these extended Q-value functions, these universal Q-value functions. We can learn again a way of estimating the variance of an infinite ensemble. And to demonstrate this, we went into the other direction. So here we are using pessimism. The task is very simple. We are this little red square, red triangle here. The direction of the triangle shows in which direction the agent looks, and the agent can go forward, turn left, or turn right. And we want the agent to navigate to one of these doors. But we don't show the same arrangement of doors every single time. We're showing like randomly chosen combinations of door colors and door positions. And then, so normally that would be it. We would just train this, and then, during training, we withhold some of these potential combinations of colors and positions of the doors so that the agent actually doesn't know what to do, or isn't supposed to be certain anyway. But then during testing, we give the agent an option. We give it basically two possible door colors as an input. That's the Z in the universal value function. And we tell it to just choose, go anywhere it wants, but it can basically decide between two possible doors. One of these doors it has seen during training, and one of these doors it hasn't seen during training. And the idea is that if the agent needs to know what it knows. It needs to know if I tell it to go either to the red or to the green door. It needs to know which of those two combinations of doors, door color and location, it has seen during training, and can therefore make any kind of reasonable prediction of. And we basically see that with the size of the neural network. So this is like, how wide is the neural network? Ideally, it would be infinitely wide, but we can't do that. Our method here in blue is outperforming in this task choice task. So the baseline where this is just an ensemble, and this is just this is an ensemble of 8, this is an ensemble of 1. And we also show that the computation time for our function is essentially the same as for an ensemble of 1. So there's not really like a lot of additional computation time that's required. Good. So this was the first way of looking at generalization. And yes, we have very little time left. However, this is what the traditional way we look at generalization. We see how similar are we to things we have seen during training. And if we're very similar, then we say our network has to be sure, right? The issue is that this does not really hold for the idea of extrapolation. So if I want to predict something over here, this kind of approach is completely useless. And this can be simply seen by the fact that the epistemic variance that I computed, like, the one where I said like the variance over the infinite ensemble can be computed in a way this thing didn't depend on the labels at all. It was completely label agnostic, and this means it makes sense why this is the case. Because if you compute upper and lower bounds with this type of uncertainty, you need to be able to basically make the statement for all possible tasks that you want to learn. But in practice, this is not very useful, because in practice, most of the time, we are basically over here, and we always get basically the very uncertain estimator. Like our agent is always uncertain over here, simply because the ensemble that learns to predict things here can't use the label information to make any predictor. So there must be something else. And we're basically coming back to the idea of invariances that I started the talk with in the beginning, where we're saying, like, we need something like, so that there must be, and this is now not in the training data X, but there must be something in the labels of these functions that allows us to make an uncertainty, like to assert that we know something about, or that we can make a reliable prediction with this network. And the basic assumption, the way that we're formalizing this is by invariances, where we're saying, if we're learning how to play chess, then there is an invariant that says if you just swap the board and swap the colors, then the game is the same. The output should be the same, right? And therefore, there is a structure, there's an invariance in the data that we want to learn. In the interest of time, I'm not going to go into too much detail here, but the easiest way of formalizing this is by saying, if an invariance is there, like if the function that I want to learn has this invariance, then I should be able to use the invariance to produce more data, more training data. Because if I'm training with all of the training data, all of the data augmented training data set, I should end up with a neural network that is also invariant to this. So here we have like a very simple example of this. We have so this is a Reacher robot. We did not use this Reacher robot. It's just here for illustration. What we did instead is we had like this situation here where this is a robot arm. The red dot is the shoulder of the arm. The black dot is the hand of the arm. And the job of the agent is to move the hand into the green dot in the middle. So this is a very classical thing, because you can just, by coordinate transformation, you can just basically make it reach anywhere. And what we're doing is we're testing, or we're training this with a subset of SO2. So SO2 is the group of all possible rotations. And we are having here, for example, C2 is the group of all 180 degrees rotations. C4 is of all 90 degrees rotations, and so forth. And what we're going to do is we're training with like a subset of these, and then we're testing it on something we have never seen before to see how well does this actually generalize. And here we're kind of using another interesting property of ensembles, and that is that, again, theoretically, for infinite width networks and infinite ensembles of them, the expectation over our ensemble becomes invariant to all the symmetry groups that were fully present in the data. I'm not going to explain why this is the case. There is a very good, like this paper here, requires a while to get through it, but it's kind of very, very insightful in that. So what we basically say is, let's use this in reinforcement learning. We're training a policy. So we're picking one of these environments here. Let's take the first one. We're training an optimal policy in it. This optimal policy sucks in this environment. because this environment is different, right? But what we can do is we can then take the policy here and we can distill it just by, training a neural network to copy it, to copy the output of it, by distilling this optimal policy into an ensemble of neural networks. And the theory says that the expectation over this ensemble should become invariant to this, to the symmetry groups that are describing the invariance of this environment. And basically, like, the short answer of this is it works. We have derived like a theoretical bound on the return, where we can bound the difference between the ensemble, like the performance. J is the symbol for the final performance of the policy. The final performance of our distilled policy after convergence. We can bound this to the optimal policy in this environment. In the test environment, I have to say, that has never been seen before. Using two terms. One of them is n is the number of, like, the size of the ensemble. And the other one, kappa, is related to how densely we sample the space of all possible, so in the symmetry group. And we can basically show that both here, if you increase the ensemble, or if you increase the subgroup size, so like how many rotations you show to the agent, in blue, the performance goes up, and in red, the total variation over orbits, which is a measure of invariance, goes down. So you basically become more and more invariant, even in samples in test environments that you have never seen before. And lastly, this also generalizes to unknown symmetry groups. So before this, here, this is a very interesting insight, but the problem here is that you usually don't know the invariances that are there in your data, right? You usually can't describe them mathematically. But the interesting thing is that the same thing holds if you don't know them. So here we have another one of these, very hard to see, but this little red triangles agents that are supposed to go to the green golds in this environment. And we don't know any of the invariances that are present here. But what we did is we first trained this with PPO. So this is the training performance on the training environments. This is the same performance on the test environment. So it's not terrible, but it's much lower. This is because you haven't seen the test environments before. And if we're using the right data set, and this is a different lecture, but if you are using the right data set, then we can actually show that this is the distilled performance. In training, it doesn't change anything. If you have n equals 1, is like one neural network, or here we have 10 neural networks. But if we are looking at the test performance, then the ensemble has actually a higher performance than the original policy. So just by using this trick, by going through an ensemble of neural networks, we ended up at a policy that generalized significantly better on environments it has never seen before. So, and last slide. So in general, the point that I want to make is that if you're using neural networks, and I know that many of you want to use neural networks because your reviewers keep telling you you should, then you kind of have to ask yourself, how can I, even if it's just a probabilistic guarantee, but how can I say anything about like how sure I am that these outputs of these neural networks are actually correct? And the first thing that everybody of you will probably choose if you've just never worked in this space is just to use an ensemble. Just look at the variance of an ensemble of predictors and then say, this is probably a good estimator. And I want to tell you that while this is provides you a lower bound on what the network actually predicts, it only works very, very close to the training data sets. This is the first part of the lecture. And the second part of the lecture is that this is not the best thing we can do. because neural networks actually excel at extrapolation. You will be surprised how good a lot of these neural networks are when you try to predict stuff that you have that's very different from your input. The problem is that these uncertainty bounds that we're getting from ensembles do not extend to this. And in practice, what we would need is we would need a different way of defining our own uncertainty over the predictions of the neural network that is more related to what kind of invariances are in the data, how do these invariances, how well did we sample these environments during training, these invariances during training, and so forth. I do have some ideas in this direction, but they're not in this talk. So if you're interested in this kind of thing, I'm happy to talk about it. But so far, nobody has cracked this nut yet. So the best thing we have actually gotten to was the previous section where I talked about like empirically just averaging over over an ensemble of neural networks. That seems to work under certain conditions. But beyond that, it's very, very hard to put like a number on this and say that in this situation, this neural network is really reliable, even though the situation is quite different from training. Thank you for listening. I have like 2 minutes or so, 1 minute for questions.
Thank you very much. Is there any quick question? 1 minute.
Maybe a quick question about the invariance. I can understand why you might want a Q function or a value function to be invariant, but why would you want a policy to be invariant in the same way, unless you've already modified the inputs for it?
You can think of it like, so in neural network, let's say, okay, very simple. You have, in the example that we had before, there was like 3 actions: go forward, move, rotate left, rotate right, right?
Yeah.
In principle, this means that there is an equivariance group, that there's basically 3 equivariance groups in this thing. One that says all of the inputs where you go forward are the same, one that says all of the inputs where you go left are the same, and one where all of the inputs where you go right are the same. This is, of course, like pretty insane. It's not going to work. But the idea is that there are probably in the data, like in the combination of observations that the robot observes and actions that the robot is supposed to take, that there should be some present invariances. Like whenever I end up in front of a door, I probably want to open it. Because why would I end up in front of the door if I don't want to open it? So it's probably so that in most of these optimal policies, after training, you should just like make your decision whether or not you want to open the door only based on the door that's in front of you and not above based on anything else that's in the room. This is really hand-wavy because, as I said, we don't know these invariances that we want this network to become invariant to. But the idea is that any true procedure in this field needs to kind of learn these invariances from the data at the same time that you are learning the functions in a way that we don't fully understand.
Okay, let's thank the speaker once again.